My name is Quentin Gargan, and I'm talking about solar photovoltaics. And I wasn't due to start until 4:15, so I actually have a sort of half an hour. But if anybody particularly wants photovoltaics, they're going to come in after 15 minutes. And we just have to see how that works out. I might, if people show up at 4:15, I might have to go back over some things. Just by way of background, I originally was involved over the last 8 years with developing PLC-based controllers. We design our own microprocessors, and we've been controlling off-grid renewable energy systems that work in areas where you simply don't have a grid, remote phone masts and other off-grid applications. There hasn't been a market for photovoltaics in Ireland up until very recently. Photovoltaic panels, though, have been around for about 50 years, primarily used in situations where it's very difficult to get electricity from other sources, such as lighthouses and remote applications. Basically, you have N-type silicon and P-type silicon, and where you get the junction between the two, when light hits that junction, it causes a flow of electrons, and the flow of electrons is the flow of electricity. It's very well understood. The technology over the 50 years has come to be well understood. Satellites, various different systems have been using them. It's known that the process degrades steadily at about 0.7% per annum. So if you have a 1 kilowatt system, you know that after 25 years it'll be producing 80% of its capacity. So it is a steady decline, but that decline is clearly understood. This has been terribly expensive, and back in 2008 we were putting in solar parks in Spain, and we were getting paid 45 cents, which was at the time 5 times the retail price of electricity for our electricity. And putting in systems like that cost about €5 per watt. We can now put in systems for 1/10. The panels cost 1/10 of what they cost in 2008, and the overall build cost is down. And the reason for this is that countries like Spain had these massive rollouts of solar farms. In fact, the largest one, this is the largest one in India. It's 3 kilometers from end to end, and it's got 2.75 million panels in it. In fact, when you see 2 people walking in front of one of these arrays of panels, you get some idea that on this massive scale, when you get to mass production, the cost of the panels comes down quite significantly. I would argue that Ireland so far has been a one-trick pony, relying on wind to meet its Kyoto obligations and its renewables obligations. And that, because you will get days when there is no wind anywhere in Ireland virtually, it requires you to have the same generating capacity as if you had nothing. So the so-called spinning reserve, which is where the grid has to keep backup available at any time, doesn't change. Whereas if you actually combine wind and solar, we always have one or the other. And so rather than trying to achieve 40% renewable energy from wind, if we were to look for 25-15 or 30-10 or some other ratio between the two, it would be more useful in terms of the grid. The area of land mass covered by these dots here is the amount of land it would take up to produce all of the world's total global energy. That's transport, heating, electricity, the lot. So it's a relatively small land mass that's required. And the material in solar panels is silicon, is sand. It's not like we're using any ingredients like lithium or precious metals that are limited in supply. So this is what you have in a typical photovoltaic system. You have a number of panels, depending on whether it's a domestic house. A typical domestic house might have 8 or 10 or 12 panels, and if they're in different directions, they'd be connected in different strings into what's called an inverter. So the panels generate electricity as what's called direct current, which is kind of electricity you see from a battery. The inverter looks at the grid, it lines itself up with the frequency of the grid, and it starts injecting the electricity from the panels into the grid. And then it gets used around the household, and if there's not enough household electricity being used, it starts exporting the surplus. So you have a situation where you have a 3 kilowatt array, 12 panels on the roof here, pushing 3 kilowatts into the consumer unit. there's nothing on in the house, so you export the 3 kilowatts to the grid. Then maybe somebody switches on a couple of loads, an electric kettle and something else, and now you're importing 1 kilowatt using 4 kilowatts, and the solar array is providing 3. And at another moment in time, you might be producing 3 using 1 kilowatt. There's just a couple of things running in the house, and you're exporting the other 2. So you're constantly either importing or exporting electricity in this manner. And at night, obviously, you have to import it all. Now, the problem with this, of course, is that if you're getting paid for what you export, it starts to make sense. In Ireland, up until 2 years ago, you got paid 9 cents for the electricity you exported. That was a scheme that was introduced by Electric Ireland 2 years earlier, but they scrapped that scheme, and since then, what you export, you give to the grid for free. You don't get paid for it. So it's very difficult to make this work until you have some sort of an incentive, either that, as in the UK, you get paid for producing the electricity, or as we had in Ireland, and as I believe we should have, where you get paid for what you export. In terms of the production of a panel, these are various different levels of light. 1000 watts per square metre would be very bright sunlight. 200 watts per square metre would be a very dull day. But you can see that the production of a panel is not that far out of being proportional to the level of light. So although you do get a seasonal shift, it's not as dramatic as it is with solar hot water. In solar hot water, your losses are constant. Your production might be proportional, but your losses are constant. So there is a degree of seasonality, and this is a typical simulation of what you would expect to get from solar panels in different months of the year, from January through to December. And you can see that, you know, in May, June, July, August, you're expected to get roughly 4 times what you would get at the lows of December and January. The worst month is December. So obviously this means that it's a perfect match for buildings that need air conditioning, people with chiller plants, and you know, sort of tourism businesses where you have a high load during the daytime. Interestingly, by the way, and probably perversely, the higher the temperature is, the lower your power gets. So actually bright, cold days. But because of this, in fact, in Ireland, we do get quite a good production because we don't have heat problems. The panels aren't getting extremely hot. This does mean that if you look at solar panels, you see them often sitting proud on a roof with a gap between them and the roof. With solar thermal, that's not a great idea, but with solar PV, actually roof integrated systems have a poorer cooling capability. Okay, so in the past, Electric Ireland had been offering 9 cents for export. That's currently been halted. In the UK, they've just the UK used to pay for producing your electricity. The problem with that model from our perspective is that it encourages you then to use the electricity as you produce it. So there's a lot of companies that have developed devices, I'll talk about one of them in a little while, that turn all your electricity into hot water rather than exporting it to the grid. So there's no benefit to the grid. But in Germany, for example, you get paid 12 cents for production, and a 4 kilowatt system would earn you between 400 and 1400 euros per annum, depending on how much of the electricity you could use yourself. In Ireland, if you didn't use any electricity, you get nothing, and your peak would be 760. We believe with a feed-in tariff you could get to a reasonable payback. We're looking for a system that provides some sort of incentive but doesn't actually make it lucrative. You know, the worst thing you could do is have a very lucrative scheme and roll out electricity at a huge PSO levy to the rest of the country. I don't believe that there's actually a need for that. But in most, our target market, to be honest, has become ticking the boxes in Part L for new residential properties, or industries that have a high base load and can use all their own electricity. And those are the only 2 situations in which in Ireland solar photovoltaic stacks at the moment. That will change. If you were to look at comparing this with solar thermal, if you were to look at a 4 square metre 2-panel system of hot water, it would produce, according to simulations, 1,800 kilowatt hours of hot water. If you were to produce that using either oil, gas or off-peak electricity, that hot water would cost you about €163 a year. But solar hot water systems need their antifreeze changed, they need servicing. The antifreeze should be changed every 2 or 3 years at a cost of between €200 and €300 to get somebody to come out and do it. So your net saving is around about, we say 63, 70, 75 euros per year. It's somewhere in that sort of ballpark. It's not as lucrative as the sales guys would have you believe. Also, there's moving parts, there's pumps, expansion vessels, there's pipe insulation. And there's a big problem, which is that when you go on holiday, or when the cylinder, when you haven't been using the hot water, the system boils and goes into stagnation. And that can cause damage and degradation of the system. And that is a part that often hasn't been done properly in solar thermal systems. So if you were looking at satisfying Part L and you were offering your clients one of two things, either a small 1 kilowatt PV system or a solar hot water, the PV system would be significantly cheaper to install. It requires no maintenance, whereas the solar thermal needs its glycol changed every 2 or 3 years. The saving would be, if we had a feed-in tariff, the saving would be there. I have to say that it's not a money spinner, but it will typically save you 80 or 90 euros per year on electricity that you will use yourself, particularly if you have heat recovery ventilation, or if the house is occupied during the day and there's laptops and TVs and loads running during the day. With solar thermal, because of your maintenance costs, the savings are somewhat less. If the house is unoccupied, if you go away for 2 weeks during the summer, it just exports the electricity to the grid, there's no harm done. Whereas with solar thermal, you get this stagnation where the system boils and puts pressure on the system and causes degradation of the glycol. The solar PV is solid state, there's no moving parts, whereas you actually have pumps, pump stations and various other moving components. So I would argue that solar thermal is probably no longer, a lot of builders are still using it because they're familiar with it, but it actually no longer makes commercial sense to either the householder or the builder. If you're looking to meet Part L of the regulations, you need to produce renewable energy of either 10 kilowatt hours per square meter from heat or 4 kilowatt hours per square meter of electricity. The reason why there's a bias in favour of electricity is because it takes roughly 2.5 kilowatts of oil or gas on the grid to produce electricity, to produce 1 kilowatt of electricity. So you have this favour because electricity is a premium energy source. It is by far the lowest cost means of Part L compliance, but also if you're designing larger properties, larger houses, it becomes a little bit silly. I don't know if anybody's worked on designing somewhat bigger houses, but you start needing 500 litre cylinders and massive, to get over the line on Part L with solar thermal becomes very difficult. It's also scalable. There are other boxes that need to be ticked on in terms of energy performance and carbon performance, and quite often you get a house that's ticking the boxes for the renewable energy component, but the EPC or the CPC are out of line. And often 1 or 2 more panels, particularly if somebody's putting in a solid fuel stove with a lower efficiency, or if there's features in the house, large north-facing windows or any other component that makes the house difficult to get over the line. PV systems are scalable. You can just add 1 or 2 or 3 or 4 more panels and the deep software until you get to the point that you've got the system working okay. Because there isn't any payment for power exported, it's quite common to put in an Immersion Divert device in the UK. This puts a clamp meter on your export from the grid, and as you start exporting from the grid, it effectively turns up and down a dimmer switch on your Immersion to ensure that you don't export any electricity. So you can get your solar hot water from your PV system, and that would make sense if you want to provide somebody with a solar hot water system. If you do that though, it does actually penalise you under the deep software. It's only viable for systems with sort of 6 or 8 panels, but it does make sense as a solar hot water and a PV system. Okay, just in terms of panels, two different main varieties. There's monocrystalline or polycrystalline. Monocrystalline is the one that's the longer established. It has these characteristic diamonds in the middle where the The crystal is cut from single round ingots and cut down to shape. Polycrystalline often has a slightly bluish tinge to it. It's multi-crystals, and it works better in diffuse light, but only very slightly. There is a very slight difference. It also works better in high temperature conditions. The most common one for domestic is an all-black panel, either in poly or mono, where you've got black frames and a black backsheet. That actually makes it a little bit less efficient, actually, because a black backsheet causes higher heat and you lose some power as a result. But it is the most common aesthetically appealing version. In terms of standards, there's a UK MCS scheme, microgeneration certification scheme, and that is the kind of the benchmark that most people are working to. There are also other standards that must be complied with, and the panels have to be independently tested, or the factory has to be independently tested and certify each panel in accordance with EN standards. The most common kind of standard that people look for is whether it's what's called a Tier 1 panel. This is a Bloomberg list. If you're building a solar park, your bankers would ask you if your panels, where your panels appear on the Tier 1 list, and your funding would depend on your panels being Tier 1 listed with Bloomberg. And so there's a sort of a list of manufacturers. Interestingly, most of the top 20 are Chinese or Asian based. China has become by far the largest producer, and they produce the best and probably the worst panels in the world. I would argue that actually, when it comes to rolling out solar, wind farms have economy of scale, because if you put a 30 megawatt wind farm on top of a mountain, it'll produce a lot more power at an economic base rather than putting small turbines in small locations where they don't work terribly well. Solar doesn't have the same sort of economies of scale. The panels cost the same, because we use all the same panels. There is a consultation process underway to look into whether there be a feed-in tariff. We don't know whether that's going to be based on production or export. We would argue that in the UK, where there has been a production tariff for households, it's fostered kind of wasteful use of the energy rather than allowing it to be exported to the grid. So, even though it's a premium source of energy, it's been dumped as heat into immersion water heaters and so forth. Okay, I'm going to flash through some of these things. Inverters are the component that connects the electricity to the grid and pushes the electricity into the grid. Uniquely in Ireland, ESB puts a few obstacles in our path, like having a unique grid standard that has to be met. The inverter gives you a readout of you can get an online readout of your power over a day. That's a particularly good day, but this is a more typical one, where you get sort of cloudy weather and you get intermittent supply of electricity. There are systems where the inverters are mounted on the back of the panel. I would argue that that's okay if you're looking at situations where there's partial shading and each panel runs as its own optimized system. But to use these on domestic houses, the one part of a system that may well fail over the 25-year lifetime of the panel is the inverter, and it might not be a technical fault. It could be a power surge or lightning hit or anything like that. And you have to consider, if you're using micro-inverters, whether you want to put your inverters up on the roof where when they fail you have to get scaffolding to replace them. Personally, I favour string inverters, and if you have a partial shading issue, it can be resolved with using optimizers on each panel. The optimizer isn't connected to the grid. It's a low voltage, low current device that optimizes each panel. And so it allows you to have partial shading on some panels, not affecting the entire array, but it doesn't suffer lightning surges and so forth. In terms of roof mounting, we've seen a lot of practices in Ireland where people are using these kind of bolts to just drill through the tile or slate, and then it gives you a threaded bar that you can hang the panels on. HomeBond have recently actually blacklisted that and no longer prove it. And most tile manufacturers are horrified that you would rely on this rubber washer because what happens is you get wind buffeting and it causes tiles to crack, or else it causes failure of this water seal. Either way, the roof becomes compromised. The right way to do it is to put a roof hook on the roof that is attached to the rafter with a clearance over the tiles. And then there's a foam that catches drips and a plastic strip that goes over it, and you end up with this, with the tiles or the slates cut around it, and a waterproof seal, but you can bang all you like on this. It's not in contact with any of your tiles or slates. And that's probably the only way that it should be done, either retrofitting or fitting onto roofs. Then these roof hooks take rails, the panels are clamped onto the rails, and you have the finished system. It's also, probably if you look at the history of solar thermal, you will have seen panels were always sitting proud on the roof, and then we moved to roof integrated. I think it's likely over time, for aesthetic reasons, that you see roof integrated. There's less wind loading, but because the panels run at a higher temperature, it does slightly reduce the output from the panels, but it is much more aesthetically appealing. There are very low cost ways of mounting onto corrugated iron, trapezoidal steel. Typically with these systems you could have a system installed for as little as €1 per watt. So you could have a 10 kilowatt system installed on a roof for about €10,000. Standing seams, there's brackets for that as well. I'll pass over that, but I do think that for industrial users looking at putting in PV, it is worthwhile to do energy monitoring to see what your consumption trends are. Your utility company can provide you this information in half-hour chunks, but that may not give you an exact picture. It is possible for about €100 or €120 to get a very simple monitoring system that sends data to the cloud, giving 1 minute data, and that provides much more accurate information. It's just little clamps that go onto each of the phases coming into the business premises. And when you then know, your power consumption and understand the trends, for example, the super value will have lights and fridges and freezers running all day long, but there'll still be peaks and troughs. But when you know what your base load is, you can design a system and know exactly what your savings will be. And you can work on matching your production to consumption. But there are companies now working on, developing systems that bring loads on according to how much surplus electricity you have. So, when you're exporting electricity, you run a cooler. Typically a refrigeration company can have its chilled products anywhere between 1 and 4 degrees, and they can bank. It's a cheap battery is to bring your chiller down a little bit more. On flat roofs, there are very economical mounting systems that are ballasted rather than penetrating the roof. These compromise, the optimum angle for a solar panel is 35° facing south, but if you try and do that on a flat roof, you'll need either huge ballast or you'll need to drill through, you need to through bolt to something solid on the property. So it's quite popular to have either east-west systems which have almost no wind load, or low pitch south-facing systems with low wind load. It does cause a compromise. You're looking at, if you go for an east-west system at a 10-degree slope, you're losing 16.5%, but it may well be cheaper to put in 16.5% more modules. When these modules were costing us €800 each, we spent a lot of money in the mountains getting them placed in the perfect angle, and we sometimes see specifications done for buildings sort of 5 or 8 years ago where people are still thinking that way and looking for panels to be optimized at the right pitch. It's not worth doing it when the panels are €150 a pop. This is a Solion. It's a flat roof mounting system that has very low wind load, so the ballast is actually very small because they've improved the aerodynamics of the system, and the wind as it blows is pushing the panels down rather than causing any amount of lift. So there are various different versions of that. I'll skip through the Part L calculator, but we do on our website have a calculator that you can work out the energy according to the SEAI. It's not a true version, but that's what we enter into the deep software, and we can help you with that. But we also have PV System, PV Sol, which are much more reliable industrial simulations that you can key in, the roof orientation, the pitch, the geographic location, and it gives a very accurate prediction of the power that you'll get. You get average hourly production, throughout each month and each hour of the day. That sort of information is very easily obtained, and you get these reports showing you what your monthly production will be, etc. So I'll leave it at that for now. Does anybody